Richie's going to talk to us about differentiating and integrating with ZX diagrams. Thanks.
Alex, can you guys see the screen?
Yeah.
Yeah. I couldn't get it to like zoom exactly the right size, so it's going to have to be like this. So thanks everyone. So today I'm going to talk about differentiating and integrating in ZX calculus. This is joint work with Honey, and we both work at Cambridge Quantum. So yeah, a quick outline. As you all know, ZX calculus is a powerful tool for doing calculations. It's a sort of algebraic tool, you could say that. But it's lacking in, there's still things it can't do. So for example, we can't differentiate and integrate arbitrary ZX diagrams. If we can do that, then we can do all sorts of things. For example, we can do quantum machine learning and analyze quantum machine learning phenomenon, such as Barren plateaus in ZX calculus. We could have like a ZX Taylor series. We could have ZX Fourier transforms. We can express Schrodinger's equation in ZX calculus and many other things. So this is the motivation of why we're doing this in the paper. Before I talk about the paper itself, I'd like to talk a bit about kind of the history or the progression of like developing differentiation in ZX calculus. So in my master's thesis, supervised by Stefano Goggioso, we started differentiating things such as phase gadgets and Pauli gadgets. And it's all based on our idea that we can kind of modify the Z spider as a Pauli exponential, and using the derivative of the generator here, the one-legged parameterized spider. In our paper, we use a slightly different definition, but using this, we can differentiate larger diagrams composed using these parameterized gates. And we even had the linear rule, product rule, and chain rule worked out. So we were able to differentiate arbitrary ZX diagrams into sums of ZX diagrams. So if you had a diagram with multiple occurrences of a single parameter, when you differentiate with respect to that parameter, you'll get a sum of diagrams out of the product rule. However, because we had sums of diagrams, it wasn't, and ZX calculus didn't have many rules for manipulating sums of diagrams. After derivative, there wasn't much you can do with the sums of diagrams. You couldn't do further manipulation or further, compilation of the results, for example. Later on, Zhao et al. Started looking at analyzing the Barren plateau phenomenon using ZX calculus, and they were the first people to start, say, taking a ZX diagram which expresses a quantum circuit, and then expressing the derivative and the integral in terms of a single ZX diagram. This is really good because after differentiating and integrating, you still get a single diagram, and you can then apply the rules of ZX calculus that we all are familiar with to do calculations. However, because they only had rules for circuits with a single occurrence of a parameter, they couldn't do kind of more complex calculations directly within ZX calculus, such as the calculation of the variance of a quantum circuit's derivative. And in parallel, I continue building upon my work in my thesis with Alexis, Giovanni, and myself, and we started putting a categorical kind of framework for differentiating monodal diagrams. So it wasn't just ZX calculus, we also differentiated kind of matrices over semi-rings and so forth. And we implemented this theory into DiscoPy. So, but still we didn't know how to differentiate arbitrary ZX diagrams in terms of a single ZX diagram, which is, we know is something that's possible, but we hadn't done yet. So this was something that a lot of people asked us whether we could do it. And this is kind of the main result of the paper. So the main result of this paper is differentiation of arbitrary ZX diagrams. We also provide rules for, well, we derive these rules for how to integrate circuit-like ZX diagrams with up to 3 occurrences of a parameter. Using these sets of rules, we derive the expectation and variance of a quantum circuit's gradient within ZX calculus. As example, to do the analysis of the Barren plateau phenomenon. Oh, someone's asking what the square bracket in the diagram means. So I should have said sooner. So I think here I didn't put the D here, but the square bracket means differentiate. But I think later on it's all explicit anyway. So hope it clears that out. Yep. So before I talk about the proofs and the results, I have to talk a bit about algebraic ZX calculus. So I know not everyone here has done a lot or worked with a lot with algebraic ZX calculus. So I'm gonna try to explain the rules briefly and motivate the reason why we use algebraic ZX calculus in this paper. So as we all know, the original ZX calculus is very powerful, but it's even though it's universal and complete, it's not very natively good at representing arbitrary linear maps. And the reason for that is the original ZX lacks a way to directly encode arbitrary complex numbers. Instead, it's good at natively encoding complex exponentials. So to deal with this problem, we introduced the green box, which is kind of a more general version of the green spider that we're normally familiar with. So here, instead of having an e to the I theta, we replace it with a, and where a can be any complex number. And the rules are quite similar. Oh, yes. So here's how you express the original Z spider and ZX calculus in terms of a green box. As I said, it's just replacing the alpha with an e to I alpha, and the unparameterized Z spider can be expressed as a green box spider with a 1 on it. Similar to the normal Z spider, we have the fusion rule, but instead of adding the phases, we multiply the phases, because when you multiply exponentials together, you're actually adding the exponent. And here we don't have the exponential, so we just directly multiply these numbers together. Yes. So so these are the Z spider and the W spiders from ZW calculus. And when I was writing this paper, I was told by someone that one of the motivations of developing ZW calculus is to be able to handle both multiplication and addition within the same framework. So you kind of have this ring-like structure. So, and this makes it easier to do certain calculations and show completeness and so on. And so naturally, we want to have this kind of capability within ZX calculus. However, it's not that easy to represent the W spider within the original ZX. On the other hand, in algebraic ZX calculus, we introduced this yellow triangle gate, and using this yellow triangle gate, we're actually able to give very concise decompositions of various gadgets from other graphical calculi. So you can decompose the W spider and the AND gate, for example, such as this. What do I want to say? Yes, so this is good. Although there's translations between all these calculi, it seems like when we translate gadgets from other calculi to algebraic ZX, you get this kind of internal low-level representation using the yellow triangle. But on the other hand, when you translate the yellow triangle to other calculi, you get this very large diagram. So to me, it seems like algebraic ZX is the right way to do these general problems, because it gives you compact representations of many different types of gadgets. So it gives you the benefits of ZX and ZW calculus, for example, within a single unified framework. Let me talk a bit more about the triangle itself. There's a bunch of rules, but I wouldn't worry about learning for the rules for the sake of the talk. I'm just showing them to show you what it does. And I'll explicitly point out when the triangle rules are used, and you can just believe me that I used it correctly. So the triangle you can think of as a change of basis. So when you get the 0 state, it maps the 0 state to the 0 state. It maps the 1 state to the plus state, so the Hadamard state. And then it also acts as the successor function. The transpose of the triangle acts as a successor function to the single-legged green box. And yes, the triangle is invertible. Here are some lemmas that you can prove using the rules of algebraic ZX calculus. When the yellow triangle commutes with the red node, you transpose the triangle, and when you commute the triangle with the green pi, you actually invert the triangle, and the transpose of the triangle stabilizes the one state. This rule, I'm sure everyone knows about this rule. I just had to screenshot it because it's in the way. So now we move on to the W spider. The W spider can be from ZW calculus can be represented like this compactly within algebraic ZX calculus. And as you know, many of you know, the W spider has these nice properties of symmetry, associativity, and it also can copy through these green boxes like this. Particularly because of the associative rule, we can kind of write a nesting of W spiders as a single multi-legged W spider. And the interpretation of a W spider in terms of linear maps is that when you if you have a multi-legged M-legged W spider and you put the zero state in, you get the all zero state. And if you put the one state in, you get something that is the superposition of many computational states, where these computational states are all zero except one position where it's one. So in the n equals 3 case, you might get, when you put 0, you get 0, 0, 0 in. And if you put the one state in, you get 1, 0, 0, 0, 1, 0, and 0, 0, 1. This will be important later because it turns out this property of the W state is closely connected to differentiation in the product rule. Here's a small example of how to do some calculations within algebraic ZX calculus. So in the n equals 2 case, this W state can be written as a cup with a red pi on it. And the way you do this is you use the definition, expand the definition of the W spider. You apply the pi copy rule. You then, I'm going to show this now. You're going to push the red pi through the triangle and it becomes a green dot as per the rules. And then after some fusion, you get the cup with the red pi on it. Now, let's talk about differentiation. So to differentiate ZX diagrams, you want to be able to differentiate the generators, because differentiation is a compositional thing. So if you know the derivatives of the generating functions, like when at school you learn the derivative of sine and cosine and the powers and polynomials, then you can start building them together and differentiate terms that are built within using these generators. So that's exactly what we're doing here. So as a base case, we differentiate the one-legged green spider and you get something that looks like this. You add a red pi on, and then you multiply it by this if prime theta as per the chain rule. And using some ZX manipulation, you can not just differentiate single-legged green spiders, but also differentiate any multi-legged green spiders by taking, imagine you had a multi-legged parameterized spider here. You can unfuse, you can pull out a one-legged parameterized spider out, differentiate it, and then fuse it back. So using that, you can differentiate multi-legged Z spider, and similarly, you can differentiate a multi-legged X spider by applying Hadamard conjugations. Let me show a more concrete example. So here's how you derive the parameter shift rule. So when you do quantum machine learning, when you use the gradient shift rule, the parameter shift rule, you're actually differentiating the Z gate, not just the single-legged green rotation, but you're actually differentiating this doubled version of it where you tensor it with its complex conjugate. So when you differentiate this whole diagram, you need to apply the product rule because there's two occurrences of the parameter. So you first have to differentiate this term at the top and then this term at the bottom. So when you differentiate the top term, as I said, With the multi-leg spider, you still stick a pi onto it, and you multiply the scalar as per the chain rule. So when you have a green box attached to a red pi, that is actually a scalar. So this is just a scalar I. And for the second term, you get something very similar. You get the red pi at the top, and you multiply it with minus I because there's a minus here. So you need to use the chain rule. Now we can express the derivative of this diagram on the left-hand side in terms of sums of diagrams. However, like I said, we can't do much with this because ZX calculus is not good with sums. So to make this better, we want to express the sums of diagrams in terms of a single diagram. Now, how do we do this? The idea is to do diagrammatic factorization. So you want to pull out parts of the diagram that are not common with each other, and you have this kind of common part of the diagram in the lower half that can be disregarded for now. And then the focus will now then be to take this top part of the diagram and express it as a single diagram. And with enough work, this can be done either through direct linear algebra or diagrammatic manipulation, which if I have time later on in discussions, I can show you. And it turns out a lot of this can be done using the normal ZX calculus rules, plus just one base case, that the sum of the 0 state and the 1 state is equal to the Hadamard state. So using this result and the factor out diagram, when you combine them together, you get this final result here, so that the derivative of the Z gate in the quantum circuit is equal to the ZX diagram expressed as a single ZX diagram, which in turn can be interpreted as a linear map. And it turns out this linear map is actually, this ZX diagram is actually the one diagram version of the parameter shift rule that is derived by Short et al. And this ZX result is first discovered by Zhao et al. In their paper. Now, let's look at arbitrary differentiation. So this is the key result of the paper. So we're now able to differentiate any arbitrary ZX diagram in terms of a single ZX diagram. And how do you do this? Well, first we need to think about how to represent a generalized parameterized ZX diagram. And in general, if you had a ZX diagram and you had multiple occurrences of theta, or multiple phases expressed as functions of theta, you can pull all the parameterized spiders out, and the rest of the diagram could be any diagram not parameterized by theta. It could be parameterized by other parameters, but we don't care about them because we're doing partial differentiation here. So this is the result. So to differentiate this arbitrary diagram, you just need to attach this funny looking gadget that we'll talk more about later. And I won't give the proof, but it's exactly, but I'll give the proof idea of this result. So first we note that the product rule from differentiation is very similar to the W state. And then what I mean by this is if you look at the derivative of f times g times h, it's actually equal to the derivative of f times g times h plus f of derivative of g times h and f times g times the derivative of h. Similarly, with the W state, you get this sum of superposition of computational basis states where it's all zeros except one place where it's 1. And similarly, in the product rule, you get everything is undifferentiated except in one position where it's differentiated. So it turns out we can actually take this idea and put it into practice. And if you look at this diagram, where you look at this lemma, it turns out the difference between a differentiated spider and an undifferentiated spider can be expressed as a change of basis. So if you imagine there's a parameterized spider here and here, if on the left-hand side, if it's undifferentiated, you get the original one-legged spider, and you can pull a green dot out here. Whilst if we differentiate it, you'll get something like this. You stick the red pi on and you multiply it by the scalar a, where the a is obtained from the chain rule. And it turns out this lemma is true, so you can express a differentiated phase and an undifferentiated phase in terms of change of basis. And the key is to use this transpose yellow triangle. So using this change of basis, you first differentiate all these parameterized spiders, you get this term, and then you apply the change of basis. And then after the change of basis, you get at the top something that looks like W state. And then so you replace that superposition of computational space and states with the W state. And if you do all of this, you get the result shown here. Yeah. So here's an example of it in practice, because so far we've been drawing kind of generalized diagrams. So here you have this ZX diagram that looks a bit like a graph state. To differentiate it, you just need to stick the W spider, the W state here, followed by these triangles. We don't need the green boxes because here all the parameters are just by its own. It's not a function of theta, it's just theta. So the green box becomes identity, but in other words, we don't need the chain rule. And you also need to multiply by I. As a special case of differentiating arbitrary ZX diagrams, we can express the derivative of a quantum circuit in terms of a single ZX diagram, like so. So like I said before, because there's minus theta here, we need to use the chain rule, and turns out the -1 square box is equal to the green pi box here. I just want to note that, so here we have a circuit on the left-hand side. When you differentiate it, you get something that is not actually circuit-like. So this doesn't automatically give you a gradient recipe or a parameter shift rule per se. We still need to do more rewriting of this diagram to express it as a circuit. And as a special case of the arbitrary differentiation result, we can express the previous result with the n equals 1 case. So when we set n equals 1, you actually reobtain the parameter shift rule that Short et al. Obtained. And the way to see this is if you take the W state with the pi, you can actually replace it with a single red pi as we derived earlier as our first algebraic ZX proof. And once you have a red pi here, you can just do a pi commutation rule here. So this pi kind of gets cut in half and commutes with the red pi, and this scalar disappears. Okay, so I don't know how much time I have left, but I'd like to talk about integration. There's some questions. Oh, can you always rewrite the derivative of a circuit as a circuit? So yeah, that's kind of a tricky question. So I think in general, because circuits are unitary and the derivative may not be necessarily unitary, you might have to write it as sums of diagrams. But the question is, how many sums do you need? And that is kind of the goal of doing gradient recipes. We'll talk more about this later. So I just want to show quickly the integration results. So here's the n equals 1 case. If you have a single occurrence in the expectation, you'll get a pair of phases like this. Well, you have some diagram in the middle and you can pull the phases out. And when you integrate, you simply replace these two phases with a sort of a trace, and that's the n equals 1 case. For the n equals 2 case, it's a bit more complicated. You need to write something like this. I guess the exact form is not so important, but you see that you need the triangle here, so it's a bit easier to do an algebraic ZX than regular ZX. And also, yes, we want to point out that for the variance calculation that we'll show later on, it's important to express this as a single diagram, not as a sum of diagrams, because if you took the integral of once and you get two terms, after integrating over all n variables, you get 2 to the n terms, or even in the case of that paper, I think we have 3 to the n terms. So you end up with exponentially many diagrams that so it's inefficient to evaluate. But here we get a single diagram, so 1 to the n is still 1, so that's good. Why is there no dependence on k in the integral? That's a question. So we're doing definite integration here, first of all. And it turns out if you put the k in here, it kind of just disappears. The k's kind of, the k's and the minus k's kind of cancel out. I think that's the intuition I can give for now. You can follow the calculation for the exact reason. For the n equals 3 case, you get this nice looking result that involves the W spider, and you get a trace around the W spider, which looks very general, but we actually haven't found how to do the general case so far, but we're still working on it. Okay, so as an application, I will talk very briefly about Barren plateaus, but this is not the focus of the paper, so I won't spend too much time on it. The idea is that nowadays for NISQ, in the NISQ era, applications are very QML variationally focused. So you have a circuit and you have some parameterized circuit. You need to use learning techniques to find the most optimal set of parameters to solve your problem. And the way to optimize these parameters normally is to use gradient-based methods. However, in quantum machine learning, there are these, the landscape of the loss function is often very, very wide and flat, and it's numerically difficult to do quantum machine learning on many of these parameterized quantum circuits. And this is what we call the Barren plateau phenomenon. And it turns out the way to formally describe this is that the variance of the circuit's gradient tends to 0 as the, in the general case, when you take the ansatz, as you increase the number of qubits, this sort of ansatz has a variance gradient that vanishes to 0. And in fact, it vanishes exponentially with respect to the circuit size. So in general, that means we can't really do quantum machine learning on these types of circuits. So in other words, it's very important to have techniques of detecting Barren plateaus in quantum circuits. So here we have one result that is already known, which is that the expectation of the derivative is 0. So intuitively, that means, sometimes the gradient is positive, sometimes negative, and on the average, the gradient is 0. And using the tricks we've learned from the paper, we can now do this very intuitively. I think Zhao et al. Also did this in their paper. So first of all, you take a circuit, you differentiate, so you add this kind of stick with red pi in it. That's the very, very special case that we talked about. Then we integrate, and when you integrate, you need to add a trace sort of thing around it. And when you have this wire here with the red pi connected and a trace around it, using complementarity, the pi drops out. And when you have a red pi, it's actually just 1 minus 1. So that's equal to 0. So this scalar is equal to 0. And overall, the result is equal to 0. So we get this result very intuitively. And because the expectation of the gradient is 0, we immediately get that the variance of a circuit is equal to the expectation of the gradient squared. So you know how the variance is e of x, squared minus e of x squared. One of those terms becomes 0. So now we just need to find the integral of this term. And it turns out the integral is this. And when you integrate with respect to the other variables, you then need to pull all these parameterized phases out and then apply the n equals 2 case of the integration rule. Thus, you get this kind of complicated looking diagram. And if you put a specific circuit in, then you have the variance of the whole circuit's gradient with respect to a certain parameter as a single diagram. And if you take many ansatz, you can see that this diagram is mostly Clifford, except for these triangles. So perhaps there's an efficient way to contract this diagram. In conclusion, so from the integration and differentiation results from this paper, we have new analytical tools for ZX calculus. So this potentially opens a lot of doors for trying different things in the future. For future work, we want to generalize these results to QDIT and QFinite ZX, integrate arbitrary ZX diagrams, find new gradient recipes, which is, I think, one of the questions already asked, and potentially develop new algorithms for detecting Barren plateaus in quantum machine learning. Thank you.